Hello everybody and welcome to this video. Today we want to start thinking about voltage or electrical potential energy in order to utilize it for circuit analysis that we're going to be doing in a little bit. So in order to understand voltage though, which a lot of people seem to have trouble with sometimes, what I'm going to do is kind of demonstrate a mechanical example, a real life example of uh, potential energy to be able to kind of get an intuitive grasp and be able to apply that to voltages and circuits. So to do that, we're going to go down here and look at these guys on these two different buildings. One of them is about 100 meters off the ground. The surface of the ground we'll call 0 meters, that's our reference point. And this other building is about 30 meters tall. And we have two different people on it, and they're both holding a bowling ball. And these are the same bowling balls. These are our control, because we want to see what happens if you think about gravitational potential energy and kinetic energy and things like that. Let's think about it though. I'm going to give you this. I'm going to say that the mass of the bowling ball is, for example, 5 kilograms, just to make it a nice, neat number, just like the 100 meters, to be able to do the calculations easier. So, excuse me, what's going to happen? You have this guy holding the ball 100 meters off the ground. So this ball right now though has some potential energy due to the gravitational field of the earth. The property of mass in terms of Newtonian mechanics, the Newtonian mechanics that we know, this guy has a property of mass and the earth also has a property of mass. Well, what these masses do is they exert forces on each other, which is the same exact force, and what's going to happen is they will attract each other. So let's call this guy 1 and guy 2. So this is object 1, so we say F1 onto the earth is G, and or this should be the G, or this should be the force that the ground is putting on the ball 1. So G on 1, and this is the force that the first bowling ball is exerting on the ground. And these are the same exact forces. Well, the ground is not going to accelerate much. It's going to be a very minuscule amount, but the ball is going to accelerate all the way down. And for this example, let's assume there's no air friction, just so we don't have to worry about extra math. The idea will be demonstrated. So no air friction. So no air drag. So whatever the kinetic energy of this ball is, it's not going to be affected by any resistance in the air, for this example. So what do we know about potential and kinetic energy? We know that energy is conserved, so if this ball at any point has a potential or a kinetic energy, at some later point, that must be conserved. The changes in potential and kinetic energy must be conserved. So let's write that down. Let's say U, due to gravity, the potential energy due to gravity, plus the kinetic energy initial must equal potential energy final and kinetic energy final. We know this from Newtonian mechanics. So let's see now. Initially, when we look at this first ball, it's not. I'm going to tell you this. It's not moving at t is equal to 0. It's still. It's sitting in this guy's hand. So what do we know about the energy? I want you to pause the video and kind of think about this. What do we know about anything, any terms in this equation? Okay, what we know is that it has no kinetic energy because it is not moving at all in terms of in this frame of reference that we care about. So that's going to be 0. And let's see, what do we know about the final one? We know that at the very end it's going to hit the ground, and at the very, very final portion there's going to be no potential energy from, if we call this the 0 point reference, so that's going to be 0. So we know that the initial gravitational energy must equal the final kinetic energy. And we also know that as an approximation, for near the surface of the earth, the gravitation, the potential energy due to gravitation is approximately mgh. It's a good approximation, which if you want to be more precise, you can expand that out with Taylor series for distances of, for example, meters and such, and we don't want to worry about that for this example. So that's going to be that, and the kinetic energy we know is going to be 1/2 mv squared. And what this is saying is that the energy initial must be equal to energy final, so mgh must equal to 1/2 mv squared. So what I'm going to do here is I'm going to solve for mgh and set that equal to here, and this is not for any particular problem, it's just to demonstrate about kinetic energy and potential energy. So the potential energy of this guy would be 5 kilograms times g, which is, I'll write it up here, approximately 9.8 meters per second squared for near the earth, and that is the g force due to the earth, and this acceleration due to the gravitational force of the earth. And it'll be the same for a given distance, for a given height, no matter if you have a tennis ball or if you have a truck at that same distance. They're both have the same g. Okay, so the 5 kilograms here and the g, 9.8 meters per second squared, times the height, which for this case would be 100 meters. And what we end up getting is, I'm going to put this into the calculator, you get 5 times 9.8 times 100, and we end up getting 4,000. So let me write that down. G naught is 4,900 joules, which is the unit of energy, which is newtons per, or newton meters. So in other words, let me write that over here. We have 4,900 newton meters. That is our gravitational potential energy. And if you do the same for this guy, we'll get, well, that would be UG naught. Let's label this like that. The first one and the second one, which is this guy. That would be, again, 5 kilograms times 9.8 meters per second squared times, 30 meters. So what we end up getting is 5 times 9.8 times 30 meters, which is a lower potential energy of 1,470 joules or newton meters. I'll leave it as newton meters for now, just to keep it sort of mechanical and be able to understand the relation between the distance and the force that was put on it. So we can obviously see that this guy, this ball over here, is going to have a much lower potential energy than the ball over here. And we know that if you set a reference point at this zero reference point, we call this the 0 point. This guy has a positive potential energy and this guy has a positive potential energy. And these guys will accelerate down, and assuming no air friction, they'll accelerate until the velocity is very, very, very high. So the kinetic energy is going to be very, very high. And they're just going to end up crashing down, and this guy's going to have more of an impact on the ground than this guy. And that's intuitive. There's no need to really think about that a lot in this example. So the idea here though was the reference point. So if you put a reference point of up here and call this the 0 reference point, this guy's going to have a positive potential energy, and this guy's going to have now a negative potential energy because it is below our reference point. And as we let go of the ball, it's going to get more negative and more negative until it hits the ground here. So that is kind of just to give you an example of going to use gravitation as an example of intuitive understanding for what we're going to talk about now with electric potential energy. So what we know about electricity, about point charges, if you have some positive charge and some negative charge over here, this guy's going to have some electric field emanating in every direction, and this negative electric charge is going to have the fields going into it. So we know that these guys are going to exert a force on each other due to the fields that they have. And there's also going to be a potential difference, electrical potential difference between the two, because if they're just sitting there and we let them go right now, they're gonna exert these forces on each other. But if you're just holding them, they're not gonna. If you're putting enough force on them, they're gonna be at equilibrium, and they're gonna have some potential energy. Which, if you look at the definition of potential energy from physics, it is going to be the change in potential energy from A to B divided by the charge that we're talking about. And also the integral form then would be the negative integral from point A to point B call this point A to point B, of E dot dr. And that's a electrical potential difference, and we know that the electric fields are going to be, the magnitude at least is going to be kq over r squared for point charges, where k is a constant, and that's talking about the strength of the electric field at every point between the two guys. So let's think though, we're not going to get too much in depth with the physics here. We're just going to show that they do exist, these definitions do exist. Now we're going to just look at what this means. It's talking about when you're putting these in equilibrium, we know that there's going to be a force between them, but to keep them from accelerating towards each other, you need a certain amount of energy, which you can find using that voltage equation, the potential difference equation. Now what we're going to do though here is look at the engineering one, and it's going to kind of be similar, but we're going to use it in a different way. And this is talking about the work needed to move a electrical charge from one point to another, and it's talking about the instantaneous change in the work done on the particle. So let me just draw one over here. Let's make it a positive charge. It could, or we can just make it a electron to make it more realistic, because we gotta remember electrons are what are actually moving in a circuit. So negative Q here. And to move this guy in a conductor, we're gonna need to do some work on it. And if you remember work, the definition is the force exerted on an object times the distance that you moved it. So we're gonna have some work done divided by the charge. That's going to be our voltage. So the units then are going to be, I'm going to keep it in brackets and make it a little more straight. The units of voltage is going to be 1 joule per coulomb. Per coulomb. So that means if you have 1 coulomb of charge, which is very huge, you need to exert 1 joules to get 1 volt. So 1 volt is defined as, again, if you had 1 coulomb of charge here, which is a very huge amount of charge, assuming it was isolated from the world, so you would not diffuse outwards and conduct. It's just a static charge sitting there. And to do work on that, to exert 1 volt, or to have 1 volt of potential energy for this amount of charge, you'll need to do 1 joule of work. 1 joule of work for this coulomb, for this amount of charge. So that's the definition then. And let's see what we need to take into account after that. So as far as the engineering goes though, we're going to need to only worry about something called a passive sign convention. And what that is if you have some element and there is a voltage across of it, we need to remember that, as we defined earlier, that if you have some resistor here, and which is our, it can be an element here that we drew, and we have that voltage source that we have here, the positive, we assume that since it's a conventional current, the current's going to be going this way from positive to negative, and we talked about this in the first video talking about current, and there's going to be a potential or a voltage drop across this resistor, which in this case would be the entire voltage that we see here. For example, if it was 10 volts, we'll see 10 volts across the resistor, because we're going to assume that the wires don't have any resistance for the ideal case. But in the real world, we have to remember though, wires do have some resistance, but it's usually very small, so we don't really worry about it as much. So we're going to see some voltage across it, and the polarity, what it indicates is that from a positive voltage, the positive terminal of a voltage source, the current's going to flow towards the negative, and current's going to flow from the higher potential to the lower potential. And so we're going to have this current going this way, and we got to make sure we check our signs in the we make sure we have to follow the passive sign convention that I just talked about right now. Passive sign convention, that current's gonna flow from the positive side of the terminal to the negative side, and from the positive to the negative of the element. And the issue here is that now if you want to talk about what's called power, which we'll get into the in the next video, we'll talk about power and energy. That's going to be a problem if we don't take care of our signs that follow the sign convention. So let's talk real quick about what we're going to read if we connect this to a, let's say we have a battery, and that's a positive and that's the negative side, and we're going to measure this thing over here. So if you put the probes, if you use a voltmeter or a multimeter, and we put the probe here for the positive side, measure here positive, and over here measure negative, which we won't see if I use black, so I'll use white here. Measure the negative side. And the battery is, for example, 10 volt or 9 volts to make it more standard. So what we're going to see is that it's going to read 9 volts, given that we put it this way. So that makes sense. There's if you go to laboratory, we can verify that. And if we flip the battery, flip the polarity of the battery, what we're going to read now is going to be, we'll be reading negative 9 volts now. That's what you're going to see up here. So equivalent way of showing what I just drew here, if I flip this battery, I can also say negative 9 volts over here, assuming that I didn't change my probe. So initially this was a positive, this was a negative, and this was a 9 volt supply. And then I flipped this, and as long as I flipped and put a negative sign here, this would be an equivalent statement basically. So that's another thing to remember here. I'm kind of over time again, and in the next video we'll talk about energy and power and why we need to take them into account. Thank you for watching this video.